Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with penal data modeling and that to the coverage on fixed effect model, random effect model and the method of GMM. In fact, in the last two lectures we have highlighted this particular concept. We have justified the importance of penal data modeling, and here we have to start with the various models that is attached with penal data, and that too the fixed effect model, random effect model and the generalized methods of moments. So, we like to check how is this kind of concept. So, let us see here. The usual format of penal data model is like this. We have dependent variable y and then we have independent variable x, and the simple mathematical structure is y I t equal to alpha plus beta x I t, and I t by default represents the pooling of the data by integrating both cross sectional data and the time series data, and there is a requirement of some of the basics like the covariance of these two error terms should be equal to 0, and covariance of error terms with respect to two different time periods must be equal to 0, and again some of the error terms, that is with respect to both cross sectional and time, will be equal to 0, and then finally variance of the error term should be equal to 0, which we have already highlighted in the last lecture. And in this lecture just we extend this kind of structure, and then we slightly connect to fixed effect model, then we will move to random effect model and the kind of GMM. So, corresponding to this model y I t equal to alpha plus beta x I t. So, if you move the structure is like that. Here we can estimate the models by separating its time component, so that we have t regression and that to each having n observations. For instance, we can start with like this, the extension y I 1 equal to alpha plus beta x I 1. So, that means here keeping time constant t equal to 1, if you allow I to vary, then the first model will be like this, and again when we fix t equal to 2, then the model will be y I 2 equal to alpha plus beta x I t. Similarly, you continue, then y I 3 equal to alpha plus beta x I 3. So, that means every times we are estimating the particular model with different time time periods. So, that means every years we have a estimated model where the sample observation will be cross sectional type. In the means compared to this cross sectional structure. So, we can have also time series structure where keeping I equal to 1 or I equal to 2, keeping cross sectional components constant, t can vary. So, that means we may have a structure where for every cross sectional unit we may have estimated models where the sample will vary with respect to different points of time. So, now what is happening here? So, if you go ahead with this kind of structures, then we will find the general structure is like this. So, here I equal to 1, y 1 t equal to alpha plus beta x 1 t, similarly y 2 t equal to alpha plus beta x 2 t. So, that means here I remain constant, then t will vary. So, that is technically corresponding to original model y, this one's yit equal to alpha plus beta xit. So, we have a two different flow. For instance, like this, we start with like this, yit equal to alpha plus beta xit. So, then we have, of course, there will be uit or error term. So, this has two extension. So, where I will actually keep constant and t will vary, then here t remain constant, then I will like to vary. Okay. So, this is how the different structure. So, corresponding to these ones. So, if you go ahead, then you will find. So, this is the case where I vary t constant. So, that means this part. So, if I call it here part V is this is what actually we call it. Okay. So, this is what we call actually this is the case where I fixed t will vary, I fixed t vary means this side, and then the other one here t fixed. So, that case then I will vary. So, this is how the two different structure, and accordingly we can have different levels of output. So, that means having big pool of data with respect to cross sectional units and time series units. So, keeping I remain constant, t can vary, then we have a various sets of econometrics output, that is with respect to every cross sectional unit, and again for every time series means time periods we have estimated a model where I will actually vary. So, that is how we have lots of flexibility with respect to penal data modeling. So, now taking this clue, we will proceed for the penal data modeling. So, before we start the penal data modeling, that too with respect to fixed effect models, random effect models and the GMM. So, we let us go through some kind of pool data structure. In pool data structure, we assume that alpha intercept and the residuals are constant across individual and over time. Sometimes this assumption is not a realistic one. Therefore, we will consider the models that makes intercepts or residuals change over time and across individual. So, what is happening here? We have the concept called as fixed effect model, and then we have actually a random effect models and we have GMM. In the case of fixed effect model, the variations of individual and over time is captured in the intercept, that to the entire import will go to intercept where the error component will be remain constant. So, in that case we have the structure like this. For instance, so this is intercept and this is one set of variation, that with respect to different time, and then this is another structure with respect to cross sectional types. So, this is again with respect to dummy application and this is with respect to again dummy application, and that to dummy with cross sectional unit and dummy with the time series unit. So, that means technically if I like to generalize, then the model can be rewritten like this: alpha plus summation, let us say y I w I t. So, that is one kind of case, or then another case is something like w summation delta j, then z I j. So, j equal to 1 to n plus beta x I t, and then error terms. So, this is how we can actually we can start this particular concept. So, technically we are actually bringing the time component and the cross sectional component into the systems, and then we estimate the model. So, that means we like to check the between dependent variable and independent variables, how the cross sectional unit can bring the kind of impact. Again, how the time series component can bring the impact. So, if that is the case, then every times dummy can be used for cross sectional unit and then time series unit. So, that to know whether the cross sectional unit has an impact or any time series unit has an impact. So, every times the variation will be with respect to 0 1. So, when the particular time period will be considered, then the weight will be 1, and if not, then by default it will be 0 for others. Similarly, for the cross sectional unit, then by default the entire impact will go to the intercept. That is what the concept of that the concept called as fixed effect model. So, now taking this clue, if you go ahead, then the entire structure can be written like this: WIT and ZIT are the dummy variables and defined as WIT equal to 1 for individual I, and I will vary from 1 to n, and for then equal to 0 for others. So, that means when we consider a particular cross sectional unit, that time the weight will be 1, and for other cross sectional unit by default it will be 0. Similarly, ZIT is representative for the time series component. So, when we consider a particular time period, that time period will be used as a proxy 1, and at the same time the other time periods will be treated as 0 impact. So, that is why the structure can be written actually z equal to 1 and z equal to 0. So, for instance, if you consider t equal to 1, so for the time period 1, so it will be 1, then the other time periods the effect will be 0. So, like this we have actually a extensions. That means, the simple model can be extended with lots of dummy variables by the help of cross sectional impact and the time series impact. And if the model is estimated using OLS, then we will obtain an unbiased and consistent estimator, and that's not the big deal. So, obviously, we like to check how is this particular structure. So, in the case of fixed effect model, the model has actually n into t parameters, that means n represents the number of cross sectional units and t represents the number of time elements. So, obviously, we have n minus 1 parameters of y and t minus 1 parameters of delta. So, one parameter of alpha and one parameter of beta, that will be also part of this system, and by default the degree of freedom for the entire model will be n t minus n in minus t. So, n t represents the cross sectional items and t represents the time items. So, if you multiply these two, then that will be the total sample of this panel data, and since we are taking care of degree of freedom, that with lots of dummies with respect to cross sectional unit and time series unit, by default the entire degree of freedom will be finally n t minus n and minus t. That is what the structure. So, now we will just elaborate this fixed effect concept. So, let us start with I equal to 1 and t equal to 1, and where I and t has some kind of connection. So, that means, when I equal to 1 t equal to 1, then the model will be simply represented like this. Okay. So, this is what y 1 1 equal to alpha plus beta x 1 1 and then error terms. So, when I equal to 1 and t equal to 2, then this model can be started like this. So, in that case delta 2 will be a new impact that will come into the intercept. So, likewise, if you extend t equal to t, then the delta t component will be coming into the pictures. So, that means, for the first time period, so alpha will be the kind of proxy. For the second time period, so the impact will be alpha plus delta 2, third time periods, then it will be alpha plus delta 3 and so on. So, ultimately the impact will be different with respect to different time periods. So, there is a high chance t may be t equal to 1, the intercept impact will be high, where t equal to 2, the intercept impact may be low or may be high. It exclusively depends upon the sign of this particular delta 2 and the alpha. So ultimately, this is how the kind of extension, and then we can move into the further extension where I equal to 2 and t equal to 1. Then the model extension will be like this, and y t equal to alpha plus these are the intercepts. That means actually we are moving to second cross sectional unit where t will again vary. So that means, so alpha, then the first intercept term will be added, then t will vary again. So then that times the entire impact again come to the intercept. So likewise you can extend this model. So that means there is a huge pool of extension. So now to summarize the fixed effect model where alpha is constant for all I and t. So we need to actually test the following. So that is actually obtained through F statistics. So now the F statistic actually derived through the residual sum of the square, that too with Wallace mechanisms, and then the kind of restricted mechanism. So then you will find whether f is coming statistically significant or not. If f is coming statistically significant, then by default the particular model will be very effective for the particular requirement. So now the next question is how to interpret all these parameters. Obviously the interpretation is very simple, because ultimately the impact will go to the intercept. So we can check whether it has a high weight or low weight, and then the coefficient of xi will be as usual like ordinary regression modeling. So we can actually highlight the details by taking a particular examples. So let us first move into random effect model compared to the fixed effect model. In the random effect model, variations of individual and times are accommodated in the intercept such that the intercepts change over time and across individual. In the meantime, variations of individual and times are accommodated in the residuals for a random effect model. In this case, the random error is composed into error of individual component and error of time component and error for both. And random effect model can be represented as where yit equal to alpha plus beta xit, and the error terms will be finally actually move into three different forms. One particular form is the cross sectional type, another form is the time series type, and then the pool type. For instance, we have here ui, that will be the cross sectional error, and vt, that is actually time series error, and wit is actually by pulling both cross sectional and time series. So that means in the case of fixed effect model, the time impact and the cross sectional impact will be moved into the intercept, that is taken care of through alpha, then plus minus depending upon the negative and positive impact of time element and cross sectional elements. And then finally the error component, particularly for the random effect model, same way it will move into the final error terms, that is with respect to the cross sectional error, then time series error and the pool error. So now like as usual regression modeling, since there are three error terms, so we expect the error term u should be actually mean normally distributed with the mean 0 and unit variance, and again the error term Vt, which is actually due to time component here, and it will be normally distributed with the 0 mean and unit variance, and then Wit, which is actually having a mean 0 with unit variance. So now with this structure, we like to check how is the kind of deviation. So moving into the kind of an estimation process, what we can have, the deviation effect for time series is randomly presented by BT, while deviation effect of cross sectional is randomly represented by UI. So ultimately, for random effect models, the ultimate variations of the error terms will be sigma square u, that is actually through cross sectional impact, and sigma square v, that is through actually a time series impact, and then sigma square w, that is with respect to actually pool data. So as a result, so the error a total error will be decomposed into cross sectional error, time error, and the pool data error. So that is how the partition. And in the random effect models, it means it can be estimated, the particular model can be estimated using OLS, provided if sigma square u equal to sigma square v and that 2 equal to 0. So that means both error variance for time and for cross sectional should be equal to 0. Otherwise, the random effect model is estimated using a generalized that means GLM mechanism. Instead of OLS, we have to use GLS, generalized least square methods. So that is actually with respect to two stage process. The first one is the estimate the random effect model using simple OLS technique, and then calculate RSS to estimate sample variance, and then by using sample variance estimate at the first stage, use GLS to estimate parameters of the models. That is what the structure of the random effect model, where the error variance of the cross sectional units and time units are not same, and they are not equal to, equal to 0. So in that case, we can use GLS, and by default GLS follows the two step process. By first step is the application of OLS, and second stage by the application of GLS. Then what is happening here in the random effect models, the requirement is that we like to assume that the error is normally distributed, and then maximum likelihood estimator can be used to estimate these parameters, and the parameters of random effect models are less. So it has a big big degrees of freedom, but fixed effect model has capability to differentiate individual effect and time effect. So compared to actually random effect model and fixed effect model, so if the objective is to check actually individual time series impact and the individual cross sectional impact, then my suggestion is actually the fixed effect model is the better choice. If that is not the case, then the best choice is the random effect model, where actually the kind of intercept or the individual time impact and cross sectional impact will not be actually coming into the picture. The entire weight will be taking care of that through actually the error terms. Now the issue is actually how to make a kind of choice. In what situation you can use random effect model, and what situation you can use actually fixed effect model. Of course, theoretically I have already highlighted, if you have no objective to study the individual impact of a cross sectional unit and the time series unit, then you can go ahead with the random effect models. If the objective is to know which cross sectional unit is having high impact and which time series unit is having high impact or low impact, and then in that case fixed effect is the right choice. But technically if t greater than n, that means the time elements greater than 2 cross sectional elements, that 2 with respect to size, then use fixed effect model. And if n greater than to t, so that means the cross sectional units are high than the time units, then that time the choice will be a random effect model. So use a statistical test instead of choosing between fixed effect model and random effect model. So one vital is the nature of the relationship between delta I and the x ray. That means the kind of cross sectional units, then the time series units, and then the kind of independent variables impact. If they are likely to be correlated, then it makes sense to use the fixed effect model. If not, then it makes sense to use the random effect models. Can also use the Houseman test to examine whether there is a correlation between delta I and x. Essentially, the idea is means the procedural test to see whether the regression coefficient under the fixed effects and random effect models are statistically different from each other. That means technically, if they are different, then the fixed effect models is actually a first and choice. If they are not actually different, then a random effect model is the next preference. So obviously, so we have lots of clues which can actually justify whether to take care the fixed effect models and random effect model to address the particular engineering problem, and that too as per the requirement of kind of situation. So ultimately, we have lots of options whether to use random effect models or fixed effect models, or sometimes you can actually report both the results. There is no harm at all. Ultimately, if you connect with dynamic penal data models, then sometimes the intercept by default will be removed in the process. So ultimately, it depends what is your actually the kind of objectives and how is the kind of problem structure. So looking actually all dimensions, then you have to fix what kind of model, penal data model you can pick up to solve this particular engineering problem and as per the kind of decision making requirement. So ultimately, so we can get to know what is exactly the fixed effect model and what is the random effect models and how they differentiate each other, and what situation you can use fixed effect model, what situation you can use random effect model. Sometimes there is no harm to report both the models output to address the particular engineering problem. So what will it do? So we will take a live problems and then we like to check how is the kind of estimation and how the estimated output can be used by by addressing some of the technical issues and the kind of requirement. So taking the clue of estimated outputs, we can get to know the particular difference between fixed effect model and random effect model, and we can get to know the kind of beauty of the penal data model to highlight some of the engineering problems. With this, we will stop here and we will continue in the next lecture. Thank you very much. Have a nice day.